Okay, so now that I've rocked your confidence in these examples and kind of it's a bunch of algebra and lots of little tiny details, and most of the time when students make mistakes on this process, it's going to be add, subtract, multiply, and divide, basic computational math that we've all kind of struggled with for years. But I do want to show an example of, well, maybe it's not as perfect as we think it is. And let's see if we can figure out why we have an issue going on. So take a look at this question. Anything look interesting or odd about it? It kind of looks like the same stuff we've been doing, right? So let's go through the mechanics. So the mechanics would be set up an auxiliary equation. So m squared minus 5m plus 4 equals 0. Then we factor. And so we get 1 and 4. So our complementary solution would be C1 e to the x plus C2 e to the 4x. Okay, so far nothing out of the ordinary, right? And our particular, right, is going to be of the general format of the right side. So that's going to look like a e to the x. Now, as I take the derivative of e to the x, I just keep getting e to the x. So it's going to have to look something like that, right? So I'll do my derivatives here. So that's a e to the x. My second derivative would be, shockingly, a e to the x, right? Okay. So when I substitute all those expressions in, I get, still feel like I need to point out where am I substituting this in at. So I'm taking y double minus 5y prime plus 4y. So I'm plugging in what we've discovered for that particular format. So that's a e to the x minus 5a e to the x plus 4a e to the x, right? Except what's going to happen on the left side? I get 0. So that kind of suggests that our guess about the particular format for our particular solution might not have been a good one. Okay, so why didn't it work the way we want it to, and then what are we going to do about it? Well, if you look back to the complementary solution, e to the x is actually part of the complementary solution. So it's kind of why it fell apart on us, that our particular solution is also a component of the complementary solution, whereas before this hasn't come up yet. So the workaround for this is we need to, well, be very clever and pick a different form of particular that's related to e to the x. Well, let's pick something that we've actually seen before. So let's say that maybe it looks like this. Maybe it looks like a x e to the x. And so what would our derivative for that be? That would be, I'm sorry, I said that and didn't write it. ax e to the x. Sorry, made it look like an exponent when I didn't necessarily mean to. Alright, so the derivative would be a x e to the x plus a e to the x using our product rule. And again, wow, rough day. Alright, then our double would be a x e to the x plus a e to the x plus a e to the x. Okay, so let's, I'm going to slide this over a little tiny bit. Okay, so let's evaluate now that y double minus 5y plus 4. So that would be ax e to the x plus 2 e to the x minus 5 times ax e to the x plus a e to the x plus 4 e to the x. All right, and if we combine all of these together, we eventually get negative 3a e to the x, and that's equivalent to what we had on the right side, which was 8 e to the x. Which then says a is negative 8/3. So our particular solution would be negative 8/3 x e to the x. All right, and then let's put that together with the other stuff we've got. So our general solution is c1 e to the x plus c2 e to the 4x minus 8/3 x e to the x. Okay, so as that last example illustrated, what would be smart guesses? And the answer is, well, turns out we're going to give you some of the most common patterns. So you can kind of see on this in the chart there, if your g of x looks like a certain format, here's what you want to pick for your particular solution format. So some of those that would be like a little surprising would be maybe the sine cosine ones, where we want to have a cosine plus b sine. We want to make sure we include all of those. If we're dealing with e to the x, then sometimes it makes sense to do x e to the x. And sometimes, like if you look at the number 9, x squared e to the 5x, the general particular format would be a x squared, which makes sense because that shows up in the pattern of g of x, but then you also want to think about b of x and just a c, e to the 5x. So that's sort of a hint as far as what one should try. So the next part is we're just going to practice utilizing this chart to find particular solutions of differential equations. So let's do that. Okay, so just like always, and I'm going to speed up kind of the complementary solution just so we can focus more on the particular solution. So write the auxiliary, so minus 8m plus 25, and when I solve that equal to 0, so that's going to give me m equals negative 8 plus or minus the square root, negative 8 squared minus 4 times 1 times 25 all over 2 times 1. So that's going to give me oddly imaginary solutions. And so our complementary would be e to the 4x c1 cosine 3x plus c2 sine 3x. Okay, and then we're going to, again, I want to spend more time on the particular side of this. So on the right side, I notice I can essentially factor out e to the negative x. So that's going to give me so 5x cubed minus 7 e to the negative x. Okay, so I want to go back up into that chart, kind of look for something that looks the closest to that, where I've got some function of e with some exponent polynomial, and it looks like that 9th entry, the x squared e to the 5x, is the closest format for us. So our particular solution then that we want to generalize this after would be a x cubed plus bx squared plus cx plus e to the negative x. Okay, and then notice our general format for the complementary and our general format for the particular there's no overlap between them, so we're not worried about the case where we don't have a solution that's effective. So essentially, if we go through the mechanics of this problem, we'll be able to figure out what the coefficients for A, B, C, and E are in this one. So, and that was sort of the task, was to determine the particular form. Okay, so let's jump on to the next one.